the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to continue our conversation about algebraic expressions at the level of pre-calculus. So this is not for students who are just learning algebraic expressions. This is not for Algebra 1 or Algebra 2 students, or even college algebra students. This is for those who are enrolled in a single course right before they enter into calculus. So the problems will be at a level that assume that you know trigonometry, exponential and logarithmic functions, basically everything about algebra. All right, that out of the way. Let's go into some advanced factoring techniques here for calculus. Now, I'm not telling you that each of the examples you're going to see here will occur within calculus verbatim. What I'm saying is that the styles, the thought process, what you see, the techniques used, these are all things that will be used within calculus. So let's go ahead and start right at the beginning here. I would like you to pause the video and try to factor this yourself before we start into this. Now, the first thing we need to do is think, basically, before we act in and jump into this problem. So let me highlight a couple things, or one specific thing you need to notice here. It's a pattern. And again, all throughout mathematics, patterns are critically important. So notice this is an object being squared minus an object being squared. A lot of people will multiply these two objects out, right? They'll take the first one, it's, some trinomial, and they'll multiply it out, and they'll take the second one, it's some trinomial, and they'll multiply that out. I'm telling you, you want to recognize patterns within mathematics. And so this is where that pays off. This is a difference of squares. This is some first item squared minus some last item squared. So we know it's going to be first minus last times first plus last. So let's go ahead and do that. Remember, the thing that I'm calling first is this stuff right here in yellow. And the thing I'm calling last is this stuff right here in blue. So first minus last. Probably one of the biggest mistakes is actually not paying attention to parentheses. I'm going to put a big old block of a parenthesis there, a bracket. And the first object is the 2 sine squared of x. Let me zoom in a little bit because I know my handwriting will get worse. Plus 5 sine of x plus 6. And remember, it's first minus last. So minus. And now I'm going to draw a parenthesis because you're subtracting this entire blue statement here. Not just the first term of it, not 2 sine squared, but you're subtracting 2 sine squared, and you're subtracting a negative 5 sine of x, and you're subtracting a negative 15. So it's very important that you use parentheses liberally here. So 2 sine squared of x minus 5 sine of x, and then minus 15. That's first minus last, and now we'll do first plus last. Obviously, you don't really have to write all this stuff out. It's assumed that you can do a lot of this in your head, but I'm showcasing what's going on, or what should be going on in your head as you do this. So notice that when I'm adding first plus last, I don't really bother with the parentheses. You should know that you don't need parentheses when you're adding objects. It's the subtraction of objects that matters. So here we go. First minus last, first plus last. Now I'm just going to combine like terms. And notice the 2 sine squared here cancels with the 2 sine squared there because you're subtracting. The positive 5 sine of x, it adds another 5 sine of x. So we have a 10 sine of x. And we also have a positive 6 right there, and we're going to add to it 15. Minus a negative 15 is adding 15, so you have plus 21. Double check my mathematics there. 5 plus 5, 10, yep. And 6 plus 15, 21, yep. And then I just go over to the other expression, and I say, okay, well, that is 2 sine squared plus another 2 sine squared is a 4 sine squared of x. And let's see, a 5 sine of x minus a 5 sine of x, those cancel. And a 6 minus 15 is a negative 9. Now that we've arrived at this point, you should notice you still have yet another difference of squares waiting for you, right? This is a 4 sine squared minus 9. So you can continue forward with this. Now it's not so bad, right? You have a 10 sine of x plus 21. And then you have this 2 sine of x minus 3 and a 2 sine of x and then plus 3. And that is completely factored. So that is how you would completely factor. I mean, obviously you could have multiplied all that stuff out, but I'm telling you right now, it is super important that you look for patterns in mathematics and try to recognize them as quickly as possible so that you can take advantage of factoring methods like we just did. Now let's go ahead and tackle yet another very common style of expression. It's not actually, I shouldn't say very common, but it does, stuff like this does occur. The first thing you should note is that if you're asked to factor, or if you have to factor something like this, often in calculus, it's not that you're asked to factor, it's just implied within a problem. You should note that both coefficients are divisible by 5. So I'll go ahead and factor 5 off of both those coefficients. That will leave me with a natural log to the third power of x minus, let's see, 5 goes in 100 20 times. 20 times 3 is 60, and then 5 goes into 24 times. So this is 64. E to the 3x. And that is actually a difference of cubes. If you don't see it, it is 5 times the natural log of x being cubed. I think most people would have seen that at least. And then minus a 4 e to the x being cubed. So we have our difference of cubes and the sum and difference of cubes formula. You should recall that from your Algebra 2 and your college algebra courses and your trig courses. So that should be okay. This will be 5 times the quantity natural log of x minus 4e to the x, and then natural log squared of x plus 4e to the x natural log of x, and then plus, let's see, 16e to the 2x. And people will often look at that, stare at that blankly, not knowing. If you don't know your sum and difference of cubes formula, just letting you know, you have to have those in your brain ready to go at any given moment from your college algebra course, which is your previous course, all the way through calculus. So if you don't know that, please look that up and we will move forward. I should have paused and allowed you time at the beginning of that to try that problem. Sorry about that, but we'll move forward. Now we arrive at this bad boy right here. Completely factor the following expression, and then I give a hint here by completing the square. Now this is totally all over calculus, specifically Calc 2. Completing the square is a skill that you learned back in Algebra 1, I think, and you repeatedly go through it in Algebra 2 and, so on and so forth from that point forward. But they never tell you kind of why, other than to prove the quadratic formula. There's really no reason that most students can see as to why they're using completing the square. And it ends up for very critical problems involving expressions like these. So what I'm going to do is have you pause the video, try to do completing the square on this expression if you know how to, and then we'll pick right back up and see if we can kind of fix any mistakes. Again, this is all about recognizing a pattern within this problem. And the pattern is that this is a quadratic statement. Now, normally in a calculus course, you would not be asked to do something by completing the square. They would just say, do this. We need to completely factor this. In fact, you probably wouldn't even be asked to factor. It would just be part of a bigger problem. And you have to intuitively know, I should probably factor that or do something with completing the square there. So let's see how you would understand how to do that. First thing to note is there is a pattern going on. This power right here is twice that power. So this saying that means that this trinomial is quadratic in form. It's a quadratic-like expression. And so what we're going to do, if you want to, you can always say, I'm going to let you could totally do this. You could say, I'm going to let u equal x cubed so that u squared can take the place of x to the sixth. You're more than welcome to do that. Most people probably wouldn't, but when you're first learning this, it sometimes helps to do that. So I will go ahead and do that here. Doing so, I get the following. This would be u squared minus 4u minus 525. It really doesn't make much of a difference. Coefficients are the same. It just makes it look a little cleaner. Now, completing the square. You should recall how to complete the square. You just take that u squared minus 4u, and what you're going to do is add to this expression half of this quantity right here squared. So I'm going to take 1/2 of that -4, and that's going to be a -2, and I'm going to square it. That's what I add to our expression at first. I still have that minus 525. Now, here's the deal. That green ink right there, that was not originally in the expression. So adding that green ink is a major issue. We're changing the value of the expression by doing that, so we have to offset that addition with a subtraction. Now, most people wouldn't write -2 squared, by the way. They would just write 4, but whatever. And now we are now balanced, right? We've added 4, we've subtracted 4, so we've really done nothing. We've added 0. A very common trick in mathematics is to add nothing, but in the form of something, like adding 1, subtracting 1, something like that. And so, using completing the square, we find that this trinomial, let me highlight the trinomial that I'm talking about, this trinomial right here, will factor to u minus 2 quantity squared. And then we have a minus 525 minus another 4, or in other words, minus 529. Now, if you don't notice it, that's a square right here, u minus 2 being squared. And you might hope that 529 is also a perfect square, and it is. It's actually the same thing as 23 being squared. So this is u minus 2 quantity squared minus 23 quantity squared. And you can factor that as a difference of squares. Notice that I'm constantly looking for patterns. I'm looking for that difference of squares, difference of cubes, sums of cubes. Any pattern that I can find, I'm going to take advantage of. And so this pattern allows me to say it's u minus 2 minus 23 and a u minus 2 plus a 23, right? First minus last, first plus last. And remember to do your arithmetic in the end, that's u minus 25 times u, let's see, plus 21. And remember, we did not start in the world of u's. We actually started in the world of x's. So what is u equal to? X cubed. So I'm going to go ahead and replace these u's in the end with an x cubed. So this is going to be x cubed minus 25 and an x cubed plus 21, neither of which, by the way, is a sum or a difference of cubes, so you're pretty much done. There is actually a way to factor this further. You can factor this over the irrational numbers, sorry. You could totally do that, but I'm not going to force that here. This is perfectly fine as is. So that's a good factorization. If you want to go further, you totally can, but in pre-calculus, at this point, you likely have not covered the rational roots, not the rational roots theorem, but you likely have not covered the fundamental theorem of algebra. And so factoring further here is a no-no. We'd leave it just like this. And finally, This question, completely factor yet another quadratic in form expression, right? Because the power on this term is double the power on that. So this is definitely like a quadratic expression. But it says completely factor the following expression by creating a pattern, not necessarily by completing the square. To be honest with you, it is going to be like completing the square, but it's not exactly going to be completing the square. So how do you create a pattern for this? Now, what I'm going to show you is not typically what is shown in a classroom. It's just a method that advanced students tend to pick up on pretty late in their mathematical career. So I just want to showcase something here. You have three terms. Remember, you can commute those terms any which way you want. So you could rewrite this expression in any order that you wish. And one order that you can do this in is x to the fourth plus 25 plus a 9x squared. Notice I'm leaving a space there. The reason why I'm doing that is because I would like to create out of this one right here a trinomial that is a perfect square trinomial. And that's going to be fairly easy because if you think about perfect square trinomials, let me write a few off to the side, just in like this, okay? So if you had let's pretend you had a trinomial that started with x squared and ended with 16. Okay, well 16 is 4 times 4. So 4 plus 4 would be that. And this would factor, actually let me use a different color for that so it really stands out. And so this will factor to the quantity x plus 4 and quantity squared. Let me write a different one. What if I said it was x squared plus something, I don't care what, and the end was 49? Well, 49 is a perfect square. And so I know that 7 times 7 becomes 49. 7 plus 7 is a 14. And so now if I add that green ink in, which is kind of illegal right now, but if I added that green ink in, that would factor to an x plus 7 squared. And the idea is this: if I have a squared term, or in this case, a high-powered fourth term, and a constant, I'd like to group those up and then shove in between them the number that I need to make a perfect square trinomial. So again, I'm going to go ahead and just say this is x to the fourth. I'm going to leave a big old space between those two. Notice I haven't done anything different with this trinomial yet, but what I want to do is I'm going to add something here, and then I have to offset it there. What I'm going to add is the number whose value is the sum of the factors of that perfect square. So again, just like over here, if we started with a x squared and a 16, 16 is 4 times 4. So in the middle, I put 4 plus 4x. 49, well, that's 7 times 7. So in the middle, I put 7 plus 7x. So what I'm going to do here, 25 is 5 times 5. So right here, I'm going to put 5 plus 5x. Of course, I have to offset that because that wasn't there to begin with. Oops, and it should be x squared because it's x to the fourth there, not x squared. So it's just half the power. So I put the offset. Notice the green ink, they offset each other. It's just plus 10x squared minus 10x squared, so basically adding nothing. But now, those first three terms form a perfect square trinomial that will factor beautifully. It'll be x squared plus 5n quantity squared. And a little algebra off the back end here gives me a minus x squared. And if you notice here, you have a difference of squares. This is going to be the first object minus the last object. Notice that last object is an x, not an x squared. And in the first object, plus the last object. Writing this in proper order, that's x squared minus x plus 5, and an x squared plus x plus 5, neither of which, by the way, is factorable, mainly because if you try to use the discriminant here, b squared minus 4ac is negative. So that means that neither of those are factorable, so that's as good as it gets. But there you go. That is a factored form of that x to the fourth plus 9x squared plus 25. It's a really interesting trick to use. Not a lot of people will see it. In fact, most people will just go ahead and use completing the square. Completing the square will totally work. I'm just giving you an alternative method to doing this so that you don't always have to rely upon completing the square. Still, just options that you might want to consider as you go through. I don't think that this is one that you commonly want to use, but at least the one in the previous example with the completing the square is perfectly fine. In fact, you could totally do completing the square, like I said, on this one, likewise, like you did with the last example.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.